A differentiable function, f of x, is concave up on the interval from a to b if the derivative is increasing on a to b. So graphically, a function is going to look something like this if it's concave up. So you see here, if we take a look at the tangent lines, as x gets larger and larger and larger, we see that they become steeper and steeper and steeper, but also that they are becoming positive. So here we start off with kind of a steep tangent line, but it has negative slope. So we see here that the slope is getting larger and larger and larger as x grows and grows and grows. Okay, so f that the derivative is increasing is saying that the slope is getting bigger. Another way of telling graphically that your function is concave up is that all of the tangent lines lie below the graph. Okay, obviously we'd like a symbolic way of determining whether a function is concave up or not. And we're going to use the definition, which is that the derivative is increasing. Okay, so that's saying that f prime is increasing. Well, we know that if a function is increasing, then its derivative is positive. Since f prime is increasing, its derivative is positive, i.e., f double prime of x is greater than 0. So the condition we have for f of x to be concave up on the open interval from a to b is that the second derivative of f of x is positive there. Okay, similarly, a function is concave down on an interval if the derivative of the function is decreasing on that interval. So here's what a function is going to look like if it's concave down. So if we take a look at the value of the derivative at all these points, we see that the slope, which is the value of the derivative, is getting smaller and smaller and smaller because it's becoming more and more negative as x grows. Graphically, we can tell that a function is concave down if the tangent lines lie above the curve. And symbolically, we can tell that a function is concave up if we look for where the derivative is decreasing. So this says that f prime is decreasing, and we know that a function is decreasing if its derivative is negative. F prime's derivative is negative is saying that f double prime is negative. Okay, so symbolically, we can tell that a function is concave down on an interval if its second derivative is negative there. Okay, let's do an example here. We want to determine where f of x equals x e to the negative x is concave up and where it's concave down. Well, here's the graph of x, y equals x e to the negative x. So we can see here the tangent lines lie above the curve, so the graph is going to be concave down there. But at some point, the tangent lines go to below the curve, and on that part of the graph, it's going to be concave up. Okay, by the way, the point on the graph where we go from concave down to concave up is called an inflection point. To find the x values where the graph is concave down and where it's concave up, we need to classify the sign, okay, namely whether it's positive or negative, of f double prime. So we're going to start by finding f double prime. Okay, so f prime of x, we're going to use the product rule on this. Okay, applying the product rule, we get this. If we clean it up, we get this, and then we can factor out an e to the negative x. So here we get our first derivative, e to the negative x times 1 minus x. Now we need to find the second derivative. So we're going to use the product rule again. And then we get this quantity. We can clean it up a bit, and then we can factor out an e to the negative x again. Actually, I'll factor out a negative e to the negative x. Okay, so our second derivative is negative e to the negative x times the quantity 2 minus x. Now we need to make a sign chart for f double prime of x, because we need to know where it's positive and where it's negative. A good place to start are the x values for which f double prime is 0 and f double prime is undefined. Well, e to the negative x is never 0, so the only way that f double prime is going to be 0 is if 2 minus x is 0, and that happens at x equals 2. So I'm going to put a 0 there to denote that the second derivative is 0 there. Next, we want to look where f double prime is undefined. Well, e to the negative x is always defined, as is 2 minus x, so f double prime of x in this case is always defined. Next, we're going to choose test values to see whether the second derivative is positive or negative in between these x values we just plotted. So let's start with, say, negative 10 on this side. Well, because of the negative there, we have a negative. E is always positive, so e raised to the negative 10 is positive. And then if we plug in negative 10, 2 minus negative 10 is positive. So we have a negative times a positive, which has a net value of a negative number. We don't care what it is, we just need to know whether f double prime is negative or positive. Now choose, say, 100. Well, we still have this negative there. E is still positive. Well, e to the negative 100 is positive. And 2 minus 100 is negative. So we have a negative times a negative, and that has a net value of a positive number. So this chart here classifies everywhere that the second derivative is either negative, positive, 0, or undefined. So we can read right off of it whether the function is concave up or concave down. So as we noted here, we have concave down, concave down, concave down. We didn't know this x value before. Now we know that that x value is 2. So we write f of x is concave down on the interval from negative infinity to 2. And from 2 on, we see here that our function is concave up. Finally, since the graph changes its concavity at x equals 2, we have a point of inflection there. So the point 2, to get the y value, we plug it into the original function. So when x is 2, we have 2e to the negative 2. So 2 comma 2e to the negative 2 is an inflection point. Okay, here's a problem for you to try. Find the inflection points of f of x equals e to the negative x squared. Press pause while you work on this problem. Okay, for the first derivative, you should have gotten negative 2x e to the negative x squared. And for the second derivative, you apply the product rule to the first derivative, and you get this. Okay, so what we can do is factor out a 2 and an e to the negative x squared to clean this up. So we get f double prime of x is equal to 2e to the negative x squared times negative 1 plus 2x squared. Okay, we're finding the inflection points of this function, so we essentially need to classify the concavity of it. Okay, we need to see if there are any points where the concavity changes. Okay, so we're going to plot the zeros and the undefined points of this on a number line. Well, let's just start off by noting that this is always defined, so the only thing we're going to plot on here are the zeros. E to the negative x squared is never 0, so the only zeros are coming from this piece. So if we set it equal to 0 and solve for x, we find that the two zeros are plus or minus the square root of 1/2. Now we need to choose test points in between here to find out if the second derivative is positive or negative. Okay, so I'm going to choose negative 100, 0, and 100. If x is negative 100, this quantity here is positive, and 2 times negative 100 squared is a very big number, so negative 1 plus that is going to be a positive number. So our second derivative is positive there. At 0, we have positive and negative in this case, because when we plug in 0 here, we have negative 1 plus 0. So positive times a negative is a negative number. And then when x is 100, we're going to get a positive number again. Okay, just plug it in right here. Negative 1 plus 2x squared is going to be positive when x is 100. So we have positive times positive. So since the function changes from concave up to concave down at x equals negative 1 over negative root 1 half, we have an inflection point there. Also, it changes from concave down to concave up when x is root 1 half, so we have an inflection point there. Okay, why don't you graph the original function now and take a look at what the graph looks like and point out for yourself these two inflection points. Okay, one subtlety of the definition of inflection point, it's not just any point where the concavity changes. In order for f of c to be an inflection point, the tangent line there must exist. So that would prohibit, for example, in this case, so here we have concave down, then we go concave up, but the function doesn't possess a tangent line at this point, so just because it goes from concave down to concave up doesn't mean there's an inflection point there.